Hi everyone. Let's work through a limit definition with a fairly messy function. So a lot of the work of finding the derivative using this limit definition is going to be our usual difference quotients work. So you'll find some mixed in that get a little bit messier, a little more challenging, so you can really work on those algebra skills. In this problem, we're working with a radical function, but under the radical we have k squared, our variable is squared, so that's what makes it a little bit messier. All right, so we are trying to find a prime of -2. This is the derivative of function a at the value -2. So according to the definition of the derivative, we need to set up the limit as h approaches 0 of a of, -2 plus h minus a of -2 all over h. The limit is just going to carry through these steps. Please keep it. That should show up in every step until you actually evaluate, until you're able to let h go to 0. So my very first step is going to be plugging -2 plus h into function a. So in function a, the input is represented by a k. That k is going to get replaced by -2 plus h. So I'll have the square root of -2 plus h squared minus 1 minus step 2 is to plug just a -2 in for that same k. So it's the square root of -2 squared, which is 4 minus 1, and that's all over h. I can clean up a little bit under those square roots. At minimum, I think I should be combining the 4 minus 1. But I can also do a little work under that first radical. That work will have to happen at some point, so you could save it for later. I'm just going to go ahead and do it now while I'm already rewriting a step, but you do have an option there. So limit as h goes to 0. I still haven't plugged 0 in for h, so I know I need that still. If I'm multiplying -2 plus h by itself, I should get positive 4 minus 4h plus h squared. Don't lose that minus 1. That's actually really easy to do. You're thinking about squaring carefully. That still needs to carry through as well. And then I need to subtract the square root of 4 minus 1, which is 3. I could just go with this. I'm actually going to do one more tiny step just to save me a little bit of writing. I can combine the 4 and the -1 as well. And as I'm feeling just slightly lazy about having to rewrite this whole thing, I'm going to go ahead and erase that 4 and make that a 3 and just knock out that -1. So this is what I'm working on. I'm taking the limit as h goes to 0, and as we get used to this, we'll know what's going to happen, but you can check yourself. If you let h go to 0, on the top of this fraction, you're just going to be left with square root of 3 minus square root of 3, which is 0, and on the bottom, you're also going to have 0. That 0 over 0, that's our indeterminate form. That's when we might have a removable discontinuity. And whenever we run into that, we want to consider using algebra to try and remove the removable discontinuity. So the algebra required to simplify radicals is the conjugate. Our goal here is to cancel the h out of the bottom. It's the 0 in the bottom that's giving us trouble. I can't cancel an h out of the top if all of the h's are stuck in this mess under square roots. So I'm hoping to eliminate roots, and that's where we multiply by the conjugate. So we'll take that first radical exactly as it appeared, and then we'll do plus the square root of 3 instead of minus the square root of 3. And again, if you're feeling comfortable and you can see how this is going to work when you multiply these conjugates together, it's okay to jump to that result. But until you're seeing that, please write it out for yourself and look at what happens and make sure that it makes sense. It's really important for retention that you make sure these things make sense and aren't just trying to hard memorize what the result looks like. So when I multiply these together, I'm multiplying 2 terms by 2 terms, so I'm going to FOIL that out. My first two are identical, so when you multiply that root by itself, you're squaring it, which removes the square root. So you will just get 3 minus 4h plus h squared. When you look at your outside pair, those are not identical. So we just get a mess out of that. And that's okay. We'll just write it down for now. We get a positive root 3 times the square root of 3 minus 4h plus h squared. When you're multiplying roots, you can combine them, so you could make that a single square root, but our goal is to get rid of that completely, so I'm not too worried about how we write it for this step. Next, we multiply our inside 2, and again, those are not identical, so it will not remove a square root, but this time we have a negative root 3 times the square root of 3 minus 4h plus h squared. And then our last are negative root 3 and positive root 3. Those are identical, so we're squaring the square root, which will remove it, so we're left with a minus 3. All of that is over h times the square root of 3 minus 4h plus h squared plus the square root of 3. Remember, our goal is to cancel out this h right here, so we don't want to distribute in the thing that we're trying to cancel. We need that to be factored out, and that is why I don't multiply out the bottom. On the top, the h is still trapped in a bunch of mess that I'm hoping to deal with before I try and factor it back out. Some nice things do happen in this step. That positive root 3 times our messy square root minus root 3 times our messy square root, that adds up to 0, so that's gone. The same is true for 3 minus 3. That adds up to 0, so we can wipe it out completely. And in this one, all we're left with is this negative 4h plus h squared. So we're getting really close. I'm going to factor an h out of that, remembering always that our goal, don't lose my negative sign, is to cancel out an h. So I'm leaving the bottom exactly as it is. H is already factored out beautifully. And there's the cancel I was hoping for. And then once we've canceled the h out, this is the beauty of the whole thing. We were trying to plug 0 in for h, and we couldn't do it with that h in the denominator, that lone h. But now, even though there's other h's in the denominator, when we let those go to 0, we aren't left with 0. So now we can finally evaluate the limit, which means I'm not going to write limit anymore. It's already happened by the time I'm done writing this step. So h goes to 0. Makes all of these terms drop out, and on the top I'm left with a negative 4, and on the bottom I'm left with root 3 plus root 3. So I can go a little further and add those up and say that's a 2 square root of 3 in the denominator, and then I can go a little further than that and cancel out a 2 and say I am left with negative 2 over the square root of 3. And that, to remind us where we started, is a prime, it's not quite going to fit in here, of negative 2. So the derivative of function a at negative 2 is negative 2 over the square root of 3, which, remember, derivative means slope of tangent line or instantaneous rate of change. All right, so that's all the way through a fairly messy limit definition. Again, notice that most of that work was difference quotient work. All the setup was the same as when we do difference quotients. All the simplify was the same. What's new is this last bit where we actually let h go to 0 and come up with a little bit simpler answer without any h's in it. Now that we're here, let's go on to the next piece of this, which is, can we find the equation for the tangent line? Often we have some really messy functions, and being able to approximate them with a linear function can allow us to get some decent estimates of what the curve would do without having to work with that messy formula or graph. So we want the equation to the tangent line when k equals negative 2. To get the equation for a line, we either need a point and a slope or 2 points. For calculus, when we're finding these tangent lines, we're going to have the slope, so we're going to do point and slope. The slope of the tangent line comes from the derivative. That's what the derivative does. And we've just done all that work, so that saves us backtracking and doing a whole bunch of work. What we need is the point. And if you'll remember when we started working on the visualization of a tangent line, the point is based on the tangent line touching the curve at whatever x value we're given. In this case, it's a k value, k equals -2. So to get your point, we're going to find a of -2, which is the square root of -2 squared, or 4, minus 1. And if you remember seeing that at the end of your difference quotient, you're not crazy. That does show up in our difference quotient. So we are using a value that we actually had to find earlier, but recognizing that that's what we need is important. So we need to go through the point -2 square root of 3. And if I use my point slope form, y minus y1, which is the square root of 3 from my point, equals our slope, -2 over root 3, times x minus x1. We're using k for x, so try and remember to stick with that. And our x value is -2, so this will become a k plus 2. Okay, so we should put this in slope-intercept form before we quit, which means two things. One is distributing through the parentheses, and 2 is adding that square root of 3 to both sides. So since I'm short on paper room, I'm going to do those together and hope that doesn't throw anyone too much. So the distribute gives me -2 over root 3 times k, minus 4 over root 3. If you need that reminder, if you tend to line things up not quite right sometimes, write it as a 2 over 1. We should be multiplying the 2's together in the numerator, but in the denominator, we're multiplying root 3 by 1, not by 2. And then we've added on this plus root 3. And that looks great for a final version of your tangent line. The equation doesn't have to be pretty. It can be messy like this. I don't need you to convert this to decimals unless it's a word problem where I ask for it. I would like to see these exact answers. There are things you could do to combine the 4 over root 3 with the root 3. If you want to do those, great. I think it does look even a little bit nicer, but I am quite happy if you leave it like this. Okay, I have one more part to this problem, just because it's an interesting function and I'd like to explore its graph just a little bit. So we're going to jump over to Desmos and we'll check our tangent line first, and then we'll look at some of the values of a prime and see if we can figure out what that relates to on the graph of the function. So here in red, you're seeing the function. It actually has an interesting domain. There's no values between -1 and 1, but there's these two branches heading off before and after that. And then the blue is the graph of our tangent line, and it touches right at -2. So this is what we're looking at. This looks excellent. If we start to zoom in a little bit, we are seeing that local linearity. We're seeing those two start to look pretty much identical as we get zoomed in close enough. So I'm happy with my tangent line. I've already done some of the work for filling in this table of values electronically, but I just wanted to show you that Desmos does understand function notation. So if you type in your equation using function notation, you can then type in another box, what's a of 2, what's a of 7, and you can also type in what's a prime of 2, or a prime of 7, or a prime of -1.1, and it tells you that that's the derivative. So the value of the derivative at -1.1 is -2.4-ish. And I've already moved this all up into the table so we can investigate. But you do want to be able to use technology to find the value of the derivative. We, of course, want to be able to find derivatives by hand. That's one of the core skills of this class, so that you understand the process and have some intuition if you're getting something incorrect out of technology. But it's also vital that you know how to use technology to find these values. So this is how we would do it in Desmos. Play around if you use other technology. If you have a calculator, graphing calculators in particular usually can calculate numerical derivatives, not usually with the variables, but yes, if you ask it for the value at a specific number. Wolfram Alpha will do this. There's lots of places that you can do this. So fiddle around and make sure you're comfortable doing that. What I would like you to see in this table is actually if we start in the middle, kind of close to that domain problem. So again, between -1 and 1, there are no y values. I haven't zoomed out and showed you the whole function yet, but there's nothing going on in there. So I'm going to start just shy of that, looking at the value of the derivative. So you can see if you move just to the left or right of those endpoints, you get a slope of plus or minus 2.4. If you move out a little bit more, so now I'm over at x equals -2 or x equals +2, where did it go? Right here, -2 and +2. Your derivative is a little smaller, getting closer to plus or minus 1. And as we move out, that just continues. You're getting really, really close to +1 on the right side and -1 on the left side. So I want to think about what that's actually saying. Remember, that's not your y value, that's your slope. So your slope is getting very, very close to sticking at -1. And a slope of -1 means that you're talking about a line with a slope of 1, right? If it was really constant at 1, that would be a line with a slope of 1. So I'm going to go ahead and zoom out. And here I'll turn off the tangent line for this part, maybe. There we go. Okay, so there's the function, and you can see it. This function starts to look more and more like a perfectly straight line as we head to the left or right. And what the derivative has told us is that that straight line has a slope that's getting closer and closer to 1 or -1. And what you're seeing there is slant asymptotes. That slope approaching a constant slope of -1 means the graph is approaching a line with a slope of -1. So this is actually fairly similar to absolute value. There's a weird chunk missing in the middle, but the further you get out, the more this looks like an absolute value graph. You can kind of see that as you go. All right, so I just wanted to show you that. It's kind of a cool function. Hopefully this limit definition stuff won't seem too crazy as you've been practicing your difference quotients work. Thanks for watching.